So let's say we had a limit like this. Limit is x comma y approaches 0 comma 0 of 4xy over x squared plus y squared. Well, in this case, if you plug in 0, 0, you get 0 over 0. 0 over 0, like we saw back in 21A, usually means something has to be done. In this particular kind of case, though, the thing we usually try to kind of look at first is just, does the limit even exist? Because much like before, when you have the limit from different sides not equaling each other, now we can take the limit as you literally approach, right, the point 0, 0 from any one of an infinite number of possible directions or paths. Here's where I would always start. X equals 0 or y equals 0 is a great path to use that people often forget about. So one path we could use is just to say the line y equals 0. If I sub in y equals 0 for everything, then my limit's going to become the limit, well, y is equal to 0. So I'm just taking the limit as x approaches 0 of 4 times x times 0 over x squared plus 0 squared. And normally I would just simplify this and say, well, that's the limit as x approaches 0 of 0 divided by x squared. And since x isn't 0 yet, 0 divided by x squared is just 0. This is the limit as x approaches 0 of 0, which is 0. So often 0 is a really convenient one. It almost, not always 100% of the time, but most of the time it's going to get you a value of 0. And then we just have to find some other path that is, well, we don't have to. Typically, if the limit's going to not exist, which most of these ones like this end up not existing, we have to find some other path that also goes through the point you're approaching, usually the origin, so we get a different value. And usually the thought process is you're trying to pick y equal to some function of x or x equal to some function of y, where you end up getting kind of the same highest power in the numerator and the denominator. That's kind of the best way I can say it. So I'm thinking here, if I let y equal x, well, then I'm going to have the limit as x approaches 0, right? Not xy because I'm replacing y with x. And I'm going to have 4 times x over x squared plus x squared, which is the limit as x approaches 0 of 4x squared over 2x squared. And stuff cancels to leave you with the limit as x approaches 0 of 2, which is just 2. And so since those limits aren't the same, we end up saying that the overall limit doesn't exist. So the limit xy approaches the point 0, comma 0 of 4xy for x squared plus y squared does not exist. Let me. I just had an idea that I want to kind of. I want like. No, that's fine. Okay, sure. So let's look at a few more examples. Yeah. So let's say we have the limit. Most of these ones that are not existing are usually going through the origin, just because it's really easy to come up with lots of different paths that go through the origin. So we do limit as xy approaches 0, 0. Let's say we have 8x squared times y over x to the 4th plus 3y squared. And just to kind of list out your possible options, really, usually I'm going to start with something like y equals 0 or x equals 0. And then the next place I usually go to is like y equals x. And then after that, I start thinking about different powers like y equals x squared, y equals x to any higher power, or x equals y to a higher power, or even roots, right? Roots are also good. They're not 100%, like usually odd roots are kind of the better because they kind of go all the way through the origin. But so like you can also try, I mean, usually instead of like, I really wouldn't use y equal to the square root of x typically. I would say, oh, well, that's just x equal to y squared. So don't use this, use this. So this is kind of like, but these are the usual typical paths, usually powers of x and y, linear functions of x and y. There are other options, but these are the usual choices people make. So again, I'm going to go with y equals 0 because that's easy. Limit as x approaches 0 of 8 times x squared times 0 over x to the 4th plus 0. Yeah, that's going to be 0. Top is 0, the bottom isn't. That's 0. Now, if I try something like y equals x, I don't think it's going to work. Although that's usually what I try next, right? Sometimes we're going to try things that aren't going to work. Although I will point out, I'm not following the own kind of internal rule I just set, where I said I usually try to make the top and the bottom have the same highest power. If I set y equal to x, I see that I'm going to get x cubed on top and solve an x to the 4th on the bottom. And that's not going to work out for, well, it's not that it's not going to work out. It's just not going to give me a different value. I'm going to get 8 times x cubed over x to the 4th plus 3x squared. And then if you divide everything by the highest power of x in the numerator here, you end up getting the limit as x approaches 0. Don't want to do the highest. How is it? Let's see. Do I want to do x to the 4th or x squared? Let me think here. I guess I can just factor. Yeah, sure. I can factor out an x squared from the bottom. And then you have an x squared plus 3. And you cancel those two with 2 of those. And then you're left with the limit as x goes to 0. 8x over x squared plus 3, which is 0 over 3, which is 0. Not helpful. So I really should have been saying, well, if I let y equal x squared, I'll get x squared times x squared on top, is x to the 4th, and x to the 4th on the bottom, and x to the 4th here as well. So that'll end up working out, I think. Let's check. When we do that, the limit is x goes to 0. We get 8x squared times x squared, x to the 4th plus 3, x to the 4th, and that's going to be the limit as x goes to 0 of 8x to the 4th over 4x to the 4th, which is going to be 2. Cancel the x to the 4th, which is not 0. So yeah, once again, this limit does not exist. So most of the time, when we encounter these, they don't exist, but that doesn't mean they always don't exist. So there are examples where you can show existence. And there's probably 3 ways we typically do this. There are 2 easy, quote unquote, ways, and 1 kind of hard delta epsilon sort of way, which I don't think we want to cover, at least not right now. Maybe next week if you guys really want to, but often people kind of, well, it can be hit or miss. Well, let's look at this example. The limit is y goes to 0, 0, 3y squared x over x squared plus y squared, which is still a 0 over 0 type. And now here's the thing. Usually with a limit like this, if they don't tell you, like if they just say, determine what the limit is. If it's, if the value, find the value. If it doesn't exist, tell me it doesn't exist. But if they don't tell you, usually we would start this by trying a bunch of different paths. And every path we try here is going to result in the limit of 0. So if you try y equals 0, the limit's going to be 0. If you try y equals x, the limit's going to be 0. And you're just going to keep getting 0 and 0 for whatever power or path you pick that goes to the origin. All these are going to give us a limit of 0. So usually, now, not that this is maybe the best kind of thing, but usually after I've tried like 3 or 4 things, I start to think, well, if they're all the same, maybe that actually is the limit value. One way to avoid doing quite so much work, if it makes sense to, and really it only makes sense to if you see like something like x squared plus y squared, it might make sense to convert this to polar coordinates. So we can say, well, we have seen polar coordinates, I think. We have this relationship here where if this point here is the point x comma y, where you've gone over x and up y, it's also the point r comma theta. So we have the relationship that x is equal to r cosine theta and y is equal to r sine theta. So we're going to re-describe this kind of situation using polar coordinates instead. So I'm going to rewrite this as a limit, and well, in fact, let me actually just say this. I'm going to point out if x comma y is going to the point 0 comma 0, that's going to be equivalent to r going to 0, and theta can do whatever it wants. And theta, we don't care. As long as r goes to 0, theta can be anything. So let's take a look at what happens here. We're going to get the limit as r approaches 0 of, let's say I'm just replacing things. I'm going to get 3 sine squared theta times cos. Oh, sorry, I forgot the r. Apologies. 3 times r squared times sine squared theta plus, sorry, times r times cosine theta over We know what's going to happen on the bottom here. X squared plus y squared is going to be r squared. Look at the right triangle there. So then if we simplify this, we get the limit as r approaches 0 of 3 times r times sine squared theta times cosine theta, right? I canceled the r squared here with the r squared there. And then as r goes to 0, we get 3 times 0 times some functions that aren't going to matter, because once everything's multiplied by 0, you're just going to get 0. And that's enough. That shows it. You can also use this idea to show a limit doesn't exist if it makes sense to, right? Again, I'm really only using this if I see something like x squared plus y squared, because that's going to simplify nicely. So another example here. Oh, this was, I'm trying to write numbers sometimes. Sure. So let's look at this next example. Like the limit is x y approaches 0, 0. One we already did, 4xy over x squared plus y squared. You could those zeros look lovely there. Sorry about that. So you could certainly show this one didn't exist by picking different paths that get you 0 and I think 2. Or if we try using polar, we're going to get the limit once again as r goes to 0 of 4 times r cosine theta times r sine theta all over r squared. But the problem here is that you get the limit as r goes to 0. Well, all the r's cancel. And then the limit as r goes to 0 of 4 cosine theta times 4 times sine theta. Well, there's no more r's left. So the limit as r goes to 0 is just this value again. It's like taking the limit of a constant essentially. And that's going to be 4 cosine theta times 4 times just sine theta, not 4 sine theta. And that can be any, well, not anything, but it can be different values depending on theta. So since theta can be anything, this has multiple values, meaning the limit doesn't exist. But this limit does not exist. The other way to prove or to show a limit like this actually does equal what it's equal to, often 0, is, where did I put that? Yeah. Is it the same problem? Yeah, it's the same problem. Is to do something like this. And this is where really I think this just comes from having seen it before and practicing it. Like I don't know how as a student I would come up with this on my own other than someone's like, this is how you do the thing. So where'd you go here? Let's look at this. Let's look at the same one, but from a slightly different context. So we have the limit xy goes to 0, 0 of the same thing, 3y squared x or x squared plus y squared. So we can note or observe that y squared divided by x squared plus y squared. Certainly non-negative. Could be 0, right? If y is 0 and x is not 0. It's also for sure always less than or equal to 1. Because x squared plus y squared has to be bigger than or equal to y squared. And then we can make a squeeze theorem sort of argument. We can say, well, if I take this here, then I'm going to multiply every piece of this compound inequality by 3x. This is going to give me 3x times 0 is less than or equal to 3x times y squared over x squared plus y squared is less than or equal to 3x times 1. So the thing I'm trying to take the limit of is between 0 and 3x. And then, just like before we use the squeeze theorem, if I take the limit of both of these parts, if I take the limit of x, y goes to 0, 0 of 0, I get 0. And if I take the limit as x, y goes to 0, 0 of 3x, I also get 0. So by the squeeze theorem, this middle thing limit has to also be 0. I feel like typically questions like this don't appear on midterm exams because I don't know, they feel dicey. That doesn't mean it couldn't show up. I wouldn't imagine that happening. All right, let's talk about partial derivatives. It's not really good. Yeah, no time, sure. So, partial derivatives. And the idea behind partial derivative really is that you are literally actually holding one variable constant and then differentiating the function as if it were constant. One kind of, no, actually I don't, let's just kind of look at some examples. So if we have, say, the function f of xy equal to x to the fourth plus y cubed plus x squared times y to the fifth. If I want to take the partial derivative with respect to x, I'm just going to pretend like y is a constant. That's all I'm doing. So you can write it like this, fx, or you can write it like this, del f del x, where the del symbol there just is like a slightly curlier d. No one's going to really notice if you write a del or a d, but technically partial derivatives should use the symbol del instead of d. The derivative of x to the fourth is 4x cubed. The derivative of y cubed, well, we're pretending like y is a constant, and the constant cubed is still a constant, so its derivative is going to be 0. And then here, we don't use the product rule, we use the constant multiple rule, right? You have a constant y to the fifth times x squared. The derivative is going to be the derivative of x squared, and that constant multiple just hangs out. Similarly, for the partial with respect to y, which is del f del y, or fy, same idea. Now we're letting x be the constant or play the role of the constant. I should really say we're holding x constant, what we're actually doing. So the derivative of x to the fourth is 0. Derivative of y cubed is 3y squared. And the derivative of a constant times y to the fifth is going to be that constant times 5y to the fourth. And can we simplify it? Yes. Should we? Yes, if we're going to take multiple, like we're going to take subsequent derivatives. Like we're going to take the second partial derivatives, then yeah. I mean, not that there's really much to do here, but we can write this as 4x cubed plus 2xy to the fifth. We can write this as 3y squared plus 5x squared y to the fifth. And we can take the second partials. We can find fxx, or del squared f del x squared. So I'm just going to take the derivative with respect to x of the derivative with respect to x. So looking over here, the derivative of 4x cubed is 12x squared. And the derivative of 2x times y to the fifth, or 2x times the constant, is 2 times that constant. Similarly, I want to take the second partial with respect to y, which is del squared f del y squared. Well, the derivative of 3y squared is 6y. The derivative of a constant 5x squared times y to the fourth is going to be 5x squared times 4y cubed. And yeah, I guess I would probably simplify this as 6y plus 20x squared y cubed. And then also, so typically when we're talking about finding all the partial derivatives, or not all, I mean, you could go on forever. You could do the third partial, the fourth partial, but we also usually like to find what's called the mixed partial derivatives, where you do the partial with respect to x and then y, or y then x. So here's a fun notation thing, which is actually a terrible notation thing. I can say the partial fxy, or the mixed partial fxy. That means I'm doing the partial with respect to x first and then y second. And if I want to write it using the Leibniz notation, it's going to be del squared f del y del x. Because when you read it this way, this really means the partial with respect to y of the partial of f with respect to x. So this means you do the derivative with respect to x first, and then you do the derivative of that with respect to y. So just be careful here. The notation is backwards from each other. Now, the good news, well, we'll get to the good news in a second. So if I do this, I'm going to do del y of my fx, which was 4x cubed plus 2xy to the fifth. And that's going to equal 0 plus 2x times 5y to the fourth, which will be 10xy to the fourth. Let's find the other mixed partial as well. So fyx is going to be del squared f del x del y, which is del x of del f del y, which is del x of del f del y, which was 3y squared plus 5x squared times y to the fourth. And that's going to equal 0 plus 10x times y to the fourth, And notably, they are the same. And generally, they are always the same. Now, what I should really say is, it is true most of the time that the mixed partial derivative in either order is the same either way you calculate it. There are some kind of funky functions that you can come up with that don't follow this rule. And there's something called, oh gosh, what now? Claraut's theorem, I think it's C-L-A-R-U-T, about when this is true and when it's not true. I will say that any function that looks kind of quote unquote normal, meaning like you're just writing f of x, y equals, nice powers of x, sine, cosine, trig functions, anything that's just like that is going to be totally fine. I will also tell you the kind of simplest function that I know of that violates this rule, where the mixed partials aren't equal to each other, is some kind of bonkers piecewise function. So if your function isn't piecewise, it's a very good bet that you're fine taking the mixed partial either way. You still want to show the work correctly, right? If you write fxy and then you accidentally do it the opposite way, you might kind of get marked down for that. But it's a good bet that these mixed partials are always going to equal each other. So if you accidentally do it the wrong way, you should be getting the same result. I kind of like to check them both to make sure I've not made some mistake and gotten some, like, they should end up being the same most of the time. Yeah. We'll talk about, if you guys want to, we can talk about Claraut's theorem next week. I can show you the example of, or one of the examples of a function where the mixed partials don't equal each other. It's kind of weird. Let's see. Oh yeah. Let's look at a few more examples. Let's say we had something like f of x comma y equal to x over x plus y. And we want to take all the first and second partial derivatives, meaning first with respect to x, first with respect to y, second partials, and then the mixed partials. And I think you have choices to make here. So if I want to find all the mixed partials, if I want to find fx, it might be good to write it like this. It might be preferable to write it as x times x plus y to the negative first. It's kind of up to you, right? Like you can do it either way. I'm probably going to do it like this because I don't know, the quotient rule is not terrible. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, and the derivative of the bottom is just 1 plus 0 over the bottom squared. So we know we're going to take second partials. We should definitely simplify this. That's going to be x plus y minus x all over x plus y squared, and that's just y over x plus y squared. All right, let's look at fy. I will say I generally default to writing my derivatives using this notation just because it's less writing. The same way I would write y prime instead of writing dy dx. So let's see, fy again, bottom times the derivative of the top, but now the derivative of the top is 0 minus the top times the derivative of the bottom, which is still 1 all over the denominator squared. Then we're getting minus x over x plus y squared. Now I feel like it might be a good time to rewrite these as products instead of quotients. So I'm going to write this as y times x plus y to the negative second. Right, this is negative x times x plus y to the negative second. And take the partials of those. So fxx is going to be, let's see. All right, I don't have to use the product rule here, right? Because that y is just a constant. I'm going to get y times the derivative of x plus y to the negative second is negative 2 times x plus y to the negative third. Technically, I should be, using the chain rule here and multiplying by the derivative of the inside, but the derivative of the inside is just 1. So I'm not going to worry about writing that. And then I would probably re-express this as negative 2y divided by x plus y cubed. Similarly, let's find fyy. So again, the negative x out in front of x plus y to the negative second is just acting like a constant. So you're going to have negative x times the derivative of x plus y to the negative second, literally the same thing we just wrote down up here. Let's not do the same mental work again. Like I know the derivative that's going to be negative 2 times x plus y to the negative third. So here we're getting positive 2x over x plus y cubed. Something I feel like I've said before, but I'm going to say it again. Just so you're aware, when you're taking derivatives of quotients, whether you're writing it as a quotient or not, the result at the end is that your denominator's power should always end up increasing by 1. So like if you had done this the quotient rule way and like you have to do some factoring and canceling, but like you would end up getting x like if I take like the next derivative of this, like if I did fxxx, it's after simplifying, I would end up with something divided by x plus y to the 4th. It's always the case, which is kind of neat. I suppose we should also find the mixed partials. fxy, I'm taking fx and then differentiating with respect to y. Now here I am going to have to use the product rule. So it's going to be the partial derivative with respect to y of y times x plus y to the -2nd. That's going to be 1 times x plus y to the -2nd plus y times -2 times x plus y to the -3rd. And I don't like the way this looks, right? It kind of is not my favorite. So what do I really have? I would factor out from each of these the lesser power of x plus y, meaning I'm going to factor out an x plus y to the -3rd. That is the lesser of the two powers. And I'm left with an x plus y and then a -2y. So I end up with x minus y divided by x plus y to the +3rd. It's a nice check to see if we've done things right to do the other mixed partial. And I'm going to do it using the quotient rule instead of doing it this way. The other mixed partial, fyx, which is del x of fy, y is right there. And I'm write that as -x divided by x plus y squared. So now taking the derivative that way, bottom times the derivative of the top, which is -1, minus the top times the derivative of the bottom, which is 2 times x plus y to the 1st times 1 over the bottom squared, which is x plus y to the 4th. So here, same kind of work, but a little bit different. Now I'm going to factor out an x plus y from the top. So I'm going to get x plus y times, and then I have a -1 times x plus y. And a minus, so plus x times 2, so a plus 2x. All over x plus y to the 4th. One of those cancels with one of those. And -x plus 2x is x and minus y. And yep, we got the same answer as we should. Cool. So partial derivatives, I mean, I guess I should do one more example because there's one more thing to kind of mention here. You can definitely take partial derivatives of functions of more than just x and y, right? You could, for example, have, say, f of x, y, z equal to something like x to the 4th times cosine of 2y plus 3z squared. And then we could ask to take any kind of partial. So, I mean, you're not limited, right? Someone could ask you something dumb like find f, x, y, z, z, x. Some mixed 5th partial derivative. No one's going to ask you that, but you could be asked that. But if we want to find just the first partials, right? fx is going to be easy. It's going to be 4x cubed times that constant, right? As far as we're concerned, cosine of stuff that doesn't have x in it is a constant when you're differentiating with respect to x. And constant multiples do what they always have done. They hang out. On the other hand, if we want to find the partial derivative with respect to y, then it's going to be a little more interesting. The x to the 4th is going to hang out. And then we're going to multiply by it. Well, the derivative of cosine of some stuff is going to be negative sine of that stuff. And then we have to multiply by the derivative of the inside stuff. And the derivative of the inside stuff is going to be 2 plus 0. And then fz is going to be the same sort of thing. The x to the 4th is still going to hang out in front. The derivative of cosine of some stuff is still negative sine of some stuff times the derivative of stuff. It's just that now when we do negative sine of some stuff and then multiply by the derivative of the inside stuff, now we're differentiating the inside with respect to z, and our derivative is 0 plus 6z. Cool. The other thing that we talk about here is also implicit differentiation. So yeah. Let's say we had something like this. Let's say we had x cubed plus y squared plus z to the fourth equal to 3xyz. And we are going to say that we want to find del z del x. Meaning, from this notation, it is certainly implied that z is a function of x. So this means we at least are saying we think z is a function of x. So we're going to differentiate this entire function with respect to x. So we're going to differentiate. Bugs is hitting the wall over there. Okay. With respect to x on both sides. Derivative of x cubed, 3x squared. Derivative of y squared, 0, because we're not saying y is a function of x, we're only saying that z is a function of x. The derivative of z to the fourth is going to be 4 times z cubed times the derivative of z, which is del z del x, equal to, on the right hand side, we have a product rule. We have 3x times yz, or however you want to break it up, as long as the two different functions are not in the same piece. The derivative of 3x is 3 times the other part left alone, plus 3x times the derivative of the other part is going to be y times the derivative of z, which is del z del x. And then we do the usual thing where we use algebra to solve for the derivative. So I'm going to bring all those terms to the same side. It doesn't matter which side you pick. I'm going to bring all the terms of the del z del x to the left and say I have, let's just do the work. We're going to have del z del x. We're going to have times 4z cubed and times a negative 3xy, so minus 3xy equal to 3yz minus 3x squared. And then finally, del z del x is going to equal 3yz minus 3x squared over 4z cubed minus 3xy. Now, here's a fun fact, and this is actually, I think, is kind of interesting. If you take this equation and set it all equal to 0, give myself some room here, yeah. So if you take this equation and say, I want to make x cubed plus y squared plus z to the fourth minus 3xyz equal to 0, and you call this, say, capital F. Then I will point out that capital F with derivative of capital F with respect to x is going to be 3x squared minus 3yz, and capital F with respect to z is going to be 4z cubed minus 3xy. And your partial derivative of z with respect to x, where it's implied that z is a function of x, is really equal to negative fx over fz, which is kind of cool, I think. It gives you a much faster sometimes way of finding the derivative implicitly if you want to. It's neat. I mean, and we can definitely, after we talk about the chain rule, like we'll talk about it briefly today, but next week we'll talk about the chain rule. You actually can derive how this formula works out. It's not hard to do. It's a neat little trick. But that said, let's talk about the chain rule. Chain rule is really just about drawing some pictures. So let's look at the following. Oh yeah, I think we should actually, we will look at the chain rule question on your practice exam because I feel like there's something worth observing there. But let's say we have the following function. So suppose f of x comma y is equal to x squared times e to the 3y. And we have that x is equal to cosine of t, y is equal to sine of t. x equaling cosine and y equaling sine of t are pretty standard things that people do just because it's a usual kind of parameterization of a circle. And we want to find df dt. And I do mean df dt because if you actually plugged in cosine for x and sine for y, you would have that f was just a function of t. And you can take its actual derivative, not its partial derivative. But the way we do this typically, at least the way I mean, you can do this either way, actually. You could, although I don't really want to, we could say that f of x comma y is really equal to a function of t, where we just plug in cosine of t for x and sine of t for y. And then we could take the derivative using all of our derivative skills. Our derivative would be, let's see, the derivative of cosine squared. There's some stuff squared is 2 times our stuff times the derivative of our stuff, which is negative sine, times the other piece, right? Because I'm using the product rule. Plus, then it's going to be cosine squared times the derivative of e to the stuff is going to be e to the stuff times the derivative of that stuff, which is going to be 3 times cosine of t. I don't really want to simplify it, so I'm just going to leave it like that. That's not the way you generally want to do it, though, because usually it's going to be more complicated than this, for one. The other way to do this is to draw a little picture. So we're going to say from top to bottom, f at the first level is a function of x and y. And then x and y are both functions of the same variable t. So when you read this from top to bottom, you're like, oh, f depends on x and y, x depends on t, y depends on t. So then if I want to find the derivative of f with respect to t, what I'm going to do is I'm going to find all of the paths that get me from f to t. So one of the paths is first going through x and then going to t. So that's going to be, let me just write things here. From f to x, that's del f del x. X to t is dx dt. And similarly, f to y is del f del y. Y to t is dy dt. So to go from f to t, you have to multiply all the path steps together. So we're going to get del f del x times dx dt plus del f del y times dy dt. And then we just start taking derivatives. So del f del x, I look back at the original expression, and that's going to be 2x times e to the 3y. And then dx dt is still negative sine of t. Plus del f del y is x squared times the derivative of e to the 3y is 3e to the 3y. So we get 3x squared e to the 3y. And dy dt is derivative of sine is cosine of t. Then I guess the quote unquote downside of doing it this way is that if you stop here, you've got an answer with x's and y's and t's, which is kind of weird. So you kind of need to go one more step if you want to write your answer as a function of t. But we can see that we're going to get the same answer. If we actually plug in, yeah, I normally wouldn't, but I'll plug in. I'm going to get 2 cosine of t times e to the 3 sine of t times negative sine of t plus 3 cosine squared of t times e to the 3 sine of t times cosine of t. And those parts match up, right? Up here we have our 3 cosine squared e to the 3 sine of t times cosine of t, which is the same as that. And over here we have 2 cosine of t times negative sine of t times e to the 3 sine of t. Totally the same. Totally works. So then we can ask harder things like, oh, actually, let's actually go look at this practice exam question because I want to point out, yeah. So there's something about this question I think that you should know just so you don't do too much work. So we're given this function on the practice exam for Alameda, which is that f of xy is equal to x cubed plus 2x squared y minus 2xy squared plus y cubed. And we are also given that x of t, or you can say x, is cosine of t, and y of t is sine of t. We're asked to find
the derivative of f with respect to t evaluated at t equal to pi over 2. So I'm going to point out a couple things I think we should do. First of all, we should just figure out over here that x of pi over 2 is cosine of pi over 2, which is 0. Y of pi over 2 is sine of pi over 2, which is 1. And now let's start taking the derivative. Oh, I mean, we could write the same little path. We should write the pathway. So f is a function of x and y are both functions of t. So df dt, not saying I'm plugging into, I'm just going to write that df dt without any evaluation is going to be del f del x. I do think you should write this part down unless it's actually given to you, just so that the person grading your work knows that you know what you're doing. And then start taking derivatives. So let's see. So del f del x is going to be kind of gross. It's going to be 3x squared plus 4xy minus 2y squared. That's all of del f del x plus 0 times dx dt, which is going to be negative sine of t, plus, and then we take the partial with respect to y. That's going to be 2x squared minus 2x times 2y is minus 4xy plus 3y squared, and then times the derivative sine, which is cosine of t. And now let's be smart and see what happens when we start plugging in. So if I do df dt evaluated at t equal to 0, well, again, sorry, t equal to pi over 2, apologies. I know that if I plug in pi over 2 for t, the x is going to equal 0 and y is going to equal 1. So I should just start, I don't want to actually write like 3 times cosine of t squared. That's more work than I have time to do probably. I'm just going to write that's 3 times 0 squared plus 4 times 0 times 1 minus 2 times 1 squared times negative sine of pi over 2 is going to be negative 1. I guess you could write negative sine of pi over 2, but I know it's negative. And then same deal over here. Actually, over here, I shouldn't write anything. I should just write all of this times cosine of pi over 2 is 0. I mean, you could fill it in. It's not terrible. You get 2 minus, sorry, not 0. You get 0 minus 0 plus 3. But since it's all multiplied by 0, we don't really need to worry about what any of this is here. And then simplifying this, we just end up getting 0 plus 0 minus 2 times negative 1, which is 2. So that's probably the easiest way to do this particular